Hi, everybody. Welcome. In this talk, we'll cover the mechanisms I think we should add into the Linux kernel in order to improve performance isolation. You might have seen one of these survey results. This one was published by Datadog, and it shows that for a lot of the workloads running in the cloud, a lot of container-based workloads, they use a lot less than the requested CPU that operators get for them. So systems run at relatively low utilization. Many of the world's largest companies, these are companies that have engineering resources in order to optimize their deployments, have published results showing that they're running at between 20 and 40% CPU utilization. And when I run surveys, when there's a big crowd of operators and I ask, what is your CPU utilization? I frequently get answers in that range, 20 to 40%. And some people even say that 20% is generous. They run at lower utilization. But what happened over the last few years is that some companies have been able to achieve a lot better utilizations. So for example, Google had around 35% utilization in 2011, which increased to 50% in 2019. So that's 1.5 times better efficiency that they get out of their systems. So what happened over that period of time that enabled those companies to achieve such a higher rate of utilization? Well, I've been able to find two major contributors. One are advancements in vertical autoscaling. What that means is systems that request just the right amount of CPU and memory for each workload. So systems, the orchestrators can pack in a lot of services onto servers, so that enables higher utilization. And the other side of it, the other major contributor, is the ability to perform performance isolation or handle noisy neighbors. So as you run workloads packed a lot tighter, they start to interfere with each other. So the ability to isolate performance between containers becomes critical to actually achieve this and have the users not suffer. And this is what we're going to talk about. There's been a lot of work over more than a decade about this noisy neighbor and performance isolation problem. There's been many papers from well-known universities and the hyperscalers that show us how performance interference happens and how to mitigate it. And I think there's enough out there that we can, as the Linux community and the cloud native community, can build good solutions that would enable us to also achieve utilization increases across the community, which is why I'm here. So in this talk, I want to cover these topics. I want to first explain what the noisy neighbor problem is, and I'm going to focus on the memory subsystem, cache and memory bandwidth. I'm going to talk about what software and hardware mechanisms are available to solve these problems, and then go into what's missing in Linux today in order to make this workable, and then what can we do to fix those gaps. And just to level expectations, I'm not going to deep dive into code. I'm going to more motivate the problem and then lay out what I think we should do, and hopefully we'll have a discussion later about this problem. So don't expect kind of me going into kernel code. I did my PhD in noisy neighbor mitigation, specifically network noisy neighbor mitigation. I then started a company that developed network monitoring tooling using eBPF. And we sold that company to Splunk, and I'm still a maintainer on the OpenTelemetry network collector, which we contributed. And now I'm trying to solve noisy neighbor in general. So let's start with what is noisy neighbor. When we run applications, in the cloud native community, you run these services in the cloud, but really applications map into physical servers, and applications need to share the physical resources that those servers offer. When one application consumes more than its fair share of resources, in this case, the last level cache in this diagram, then the other applications cannot obtain that resource, and so their performance degrades. And so in this talk, I'm going to focus on these two resources, the last level cache, which I'm just going to call cache, and memory bandwidth. But then at the end of the talk, I'll circle back and mention some other resources that we might also want to support for performance isolation. So how does cache noisy neighbor look like? Well, here's a diagram showing how your usual application maps into the memory hierarchy. You have the blazingly hot working set, which is in purple here, which resides in L1. And then the hot, warm, and cool working sets in L2, L3, and DRAM. When a noisy neighbor comes in, it uses the last level cache, which is shared across all of the processes on the core, uses it very aggressively and evicts your application out of caches. And now your application, instead of accessing the warm working set in L3, it has to go to DRAM, which is slower. In the more extreme example of noisy neighbor, when the noisy neighbor runs on the hyperthread on the same physical core, the hyperthread next to your application, it then also evicts your application out of L2 caches. So now your application also needs to access its hot working set in DRAM. And that hot working set, that application uses a lot. And if you look at the access times, this is from one of the Intel CPUs, at the top there, you can see that the difference between accessing memory in L2 cache and to DRAM, the difference could be substantial. It could be more than 50 times. So in theory, applications that experience noisy neighbor can run a lot slower, 50 times slower. Does it happen in practice? It turns out it does. So Google ran this test on their workloads. These are production Google workloads. And they ran synthetic noise generators in DRAM, bandwidth, memory bandwidth, and cache. And they found that for web search, which is the Google search node, they found slowdowns of up to 5 times. In ML cluster, which is a machine learning text classification system that they run in production, they found also 5 times increase in latencies. And for memkeyval, which is an in-memory key value store, like memcache, they found up to 14 times increase in latencies. So this could be massive, the difference in performance. But these noise generators are synthetic. So this is the type of noise you might expect if you're running a big data analytics system next to your workload, which most people don't. But what happens if you only have these interactive, user-facing services that are answering transactions? Are you still going to see this? To find out, we rolled out the OpenTelemetry demo. This is a demo system that has around 20 different components written in 11 different programming languages. And we deployed this onto a server and load tested it, ran a lot of load onto it, kind of medium to high load. And we found that indeed there are slowdowns. Systems experience slowdowns. Most of the services experienced around 20 to 30% slowdowns when memory was contested versus average contention for memory. And some applications experience slowdowns of around 3 times. So this actually can impact your applications. And so beyond just having users experience higher latencies, there is another effect that why we should care about this problem. Is, you have these slowdowns. These happen when there's a lot of memory contention. And the memory contention happens when the systems are under high load. What operators do when they see these slowdowns, when their users are getting service that doesn't answer their service level objectives, their SLOs, what they do is they scale out their systems. They allocate more servers to run the service. And that is just wasteful. That is expensive. You have to pay for these servers and operating them, and you run them at low utilization. So why should only the hyperscalers benefit from this, from increased utilization? We should all benefit from it. And the key to that is solving this interference and slowdowns. So what can we do to solve this problem? Well, modern CPUs have mechanisms that allow both monitoring and setting explicit limits to what each thread or process can access in the memory subsystem, both the memory bandwidth and caches. There is hardware support, which is great. Containers contain. I get this question a lot. Shouldn't containers do this for us? cgroups. Wouldn't cgroups support allocating and measuring memory bandwidth and caches? Well, in fact, they don't. There's no support right now. Luckily, there is support in a kernel subsystem called the resource control subsystem. The resource control subsystem was contributed to the kernel in 2016 and made it into the 4.10 kernel. So we've had support for this hardware for a while. And AMD in 2018 contributed support for AMD processors, which use roughly a very similar mechanism. And ARM also has support for a similar subsystem that is able to measure and control memory bandwidth and caches. And they're now in the process of contributing into the kernel patches to make the system that is currently x86, the resource control system, make it general purpose so that ARM is also supported. So how would you build a system to mitigate this type of performance interference? Well, you measure the system, you find which applications are using more than their fair share, and then you impose limits on those applications so they don't interfere with others. It's like, very simple architecture. And in fact, the hyperscalers I mentioned have published that they run these types of systems in production. So for example, Google in 2013 published that they have been running a system like this on all of their shared compute clusters as early as 2013. And Alibaba Cloud in 2020 published that they had been using a system on an order of 1 million cores for over 2 years as of 2020. So this is used in production. How could we build such a system with the resource control kernel subsystem? Well, it has 3 stages. When a new container comes up or a new service from systemd, you need to create a resource control group for it and assign all the processes from that container into the resource control group. And then iteratively, in a loop, measure what the system is, how the system is behaving, so what each group is using in memory bandwidth and caches. And then, if you need to, you adjust the limits. So these 3 activities. How do you do it with resource control? Resource control is implemented using a sysfs interface. So you write to some files in sysfs resctrl. You can create a new group by making a directory, and then you assign a process to that directory by writing the process ID or the task ID into a file in that directory that gets created for you, tasks. How do you measure? Pretty simple as well. In that directory, you have a monitor data directory, which has cache occupancy, the total number of bytes in the local NUMA node, and total memory bandwidth in and out of the current NUMA node. So great, we have this. The limits, also pretty simple. There's a file there, schemata, an inode where you can read it to see the current state. You can see 3 types of limits. MB is memory bandwidth. Here it's set to 100%. You can write 20, and it would allocate 20%. And then L2 and L3 controls, you have a bit mask where you can specify to the CPU which slices of the cache that process can run to, can evict from. So if you give it only a small number of bits on, then it can only evict from those pieces of L3 cache. So the controls are there, relatively straightforward to use. So great, why are we having this conversation? What doesn't work with this interface? Well, if you think about how memory bandwidth behaves, events happen relatively quickly in memory bandwidth. So for example, garbage collection, which is a very memory-intensive activity that processes do, that causes this kind of noisy neighbor behavior. It evicts other applications from caches. That takes between kind of a handful of milliseconds up to 100 milliseconds. And if you look at these simulations of a system, we took a system and we simulated these types of short-lived events. If you measure at 10 millisecond granularity, which is the top graph, you're able to see the events. But if you measure at 1 second intervals, which is pretty common for observability, maybe 15 seconds is common for observability tooling today, you lose all of the signal. It's just too slow in order to react to changes. You have to measure and adjust within, let's call it a millisecond. And so that's our goal, and that's what we set out to do. The problem is that resource control does not work well in the 1 millisecond regime. So here's why. You want to measure maybe, let's say you have 100 processes running on your system, and you want to measure all of them every millisecond. If it takes a few microseconds in order to measure, so making the system call and getting the results back, parsing text, then just measuring 100 processes, if you do it not in a non-parallel way, would take you a large fraction of your millisecond. And you really want to have all the measurements aligned for all the processes. You don't want to have one measuring every millisecond and then another one shifted 100 nanoseconds, 100 microseconds to the side, right? You want to have all the measurements aligned. Having this type of jitter is really bad. You don't want jitter, and you don't want to have some processes measured at different times. And so you want to parallelize. If you want to parallelize, it means that you need a process, some task, to go on multiple CPUs and read the different files from resource control in parallel. And you want to do this every millisecond. Now imagine how disruptive that would be to your system. You're trying to optimize a system that accesses memory relatively aggressively, and now you're actually you're context switching every millisecond to your process that measures and to make these system calls. So kind of this type of interface where you have to interact with resource control through user space, through files, is just inadequate in these timescales. It introduces jitter for scheduling, and it's just too expensive. Luckily, the kernel has subsystems already that support very low overhead measurement and very precise timing. So perf counters allow measuring of performance counters. The perf subsystems allow measuring of counters with very low overhead. The kernel has high-resolution timers that are able to tick every millisecond very reliably with, let's call it 5 microseconds of jitter. We've tested that. That works fine. And we have eBPF to glue everything together. So a system like this would look like you set up the high-resolution timers. They fire on all of the cores and call an eBPF program that reads the performance counters, analyzes them, and does whatever activity it needs in order to limit. So you can do all of this in eBPF. And in fact, we built a system like this, but not using resource control, using the PMU counters. So here you can see measurement of cache misses on the OpenTelemetry demo that I mentioned earlier. You can see per process number of cache misses on 1 millisecond granularity over a 500 millisecond slice. And you can see that you can find these types of events. Here you have one of the components, the OpenTelemetry collector, goes into a very intensive cache miss regime for a few milliseconds there. If you take this graph and put it on the top there and show on the bottom the total number of cache references, so that's the hits plus the misses, so all of the memory bandwidth that the system reads through the caches, you can see that indeed there's a decrease in overall throughput of the system. So this system, in SWAP, we would call it thrashing. right? You have a lot of evictions. The system is spending a lot of time just fetching from memory. It's not doing less useful work. So you can get these measurements. There are a subsystem in the kernel, but they don't support resource control. So you don't get measurements of the cache that you would have gotten. This is just per PMU. It's not the cache counters, and there's no enforcement. So what can you do about it? Well, we said that there are 3 activities that we need in order to make this system work. First is assigning containers or services into resource control groups. And there, I think we should leave this as is. Starting a new container is already expensive enough that we can context switch and interact with files like the current API calls for. But for measurement and adjustment, we need something that's lower overhead. So for measurement, I propose that we build PMU support, perf subsystem support into the resource control subsystem so that you can open perf counters and read those from eBPF. And to adjust for tuning those rate limits, instead of writing to this schemata file, I think we should add helper functions or kfuncs, and those allow eBPF programs to call into the resource control subsystem and modify the limits. It's pretty straightforward. Why shouldn't we do it? Well, first, not every CPU supports these hardware mechanisms to measure and control cache and memory bandwidth. In servers, you get mostly the higher-end CPUs. The desktops don't support it. So the fact that not everybody can use it might be a detractor for some. But ARM processors increasingly have support, and there might be kind of automotive embedded use cases. Another problem is that hypervisors don't virtualize this resource. If you go, there's a talk tomorrow, I believe, on Zen safety that deals with how the hypervisor sets these limits to the virtual machines. But the virtual machines themselves cannot control their own allocations out of their limits. So we haven't virtualized this resource, which is a problem. So right now, you need a bare metal machine in order for the kernel to have access. And finally, kind of another reason not to do it is that it adds to the user API. At least the perf subsystem, I believe, has some stability guarantees. We'll need to continue maintaining it. Luckily, kfuncs in eBPF are a type of functions that you can add that are not subject to the stability guarantees. So at least there we have some relief. But overall, I think we have hardware manufacturers have gone through the effort of adding support for these mechanisms. We already have kernel support for these mechanisms. Adding the delta of adding perf support and these eBPF helper functions to make these more usable, I think is an investment that we should make. And now I'd like to circle back to the other resources that we might want to go through and add support for in this way. I talked about resource control. There are other mechanisms. There is one other mitigation talked about in hardware, in literature, in the papers that I mentioned, on how to control noisy neighbor. What you can do is you can move the offending workload. You can pin it to a core and then scale down the frequency of the core. What happens is that noisy neighbor now doesn't have as much opportunity to create noise. It cannot evict as effectively from caches. And so you've mitigated some of it. And that is very wildly available, right? You don't need specialized CPU support. You don't need hypervisor support in order to pin a workload to a core and reduce its frequency. And here there are, I think, one of the questions you might ask is the kernel recently added support for sched-ext, which is an eBPF mechanism in order to control scheduling. I think these mechanisms are much lighter weight than writing a full scheduler just to do this. So just interact with the current schedulers and enable this. There are other resources that other systems control, namely CPU weight, which controls the relative relative importance that the scheduler gives to different processes if they compete for CPU time. So increasing a CPU weight of one process gives it more share of the CPU when there is contention. There's a similar one, I/O cost, that does this for I/O. And the memory.low governor for cgroups controls out-of-memory behavior, so which process gets evicted first. So we should consider having controls where we can very efficiently and with low overhead and very frequently adjust. The code is available under an Apache 2 license, at least for the collector that I've showed you measurements from. It's available on GitHub with that is the repo, and that has contact details. So if you want to follow up and schedule a meeting with us, everything is there. From you, if you have feedback on how to manage these types of resources, or if you want to contribute kernel code or help review it, we'd really appreciate it. If you want to run the collector, I mean, it's all open source and available to everybody. If you run it, we'd love feedback. If you want to contribute it, we'd love you to join. I hope this effort could help the community achieve the higher efficiencies. Lower cost, improve experience for users, improve the latencies that they see out of interactive systems, and overall this has kind of implications on carbon footprint and the expenditure of human effort. So I hope this will help. I'm also giving another talk later today that focuses on the mitigation effort and dives deeper into the problem itself if you're interested. And with that, thank you for coming and listening this far, and I'm happy to take questions. Yes, please.
Did you notice the TLB is also contributed to the noise enable issue?
If I noticed contributions to, sorry?
TLB missing. TLB.
TLB.
Yeah.
Some TLB misses contributions. I haven't tracked those. TLB is another source of noise in the kernel. I'm just giving some context where, as you context switch, if the TLB is not in caches, that increases the context switch cost. So there's been some advancement. I haven't tracked it. Happy to talk about it later. Ask anything, discussion. How would you implement this, if at all? All right, thank you for coming, and I'll be around if you think of any more questions. Thank you for coming.